Heisenberg's suggestion. In this video, we are going to look at what classical physics is telling us and then what Heisenberg's tool is also telling us. And this is the basics of quantum mechanics, which is very important for us to know. My name is Adams. Welcome to LIB Academy. Before we start, in our previous videos, we looked at commuting and non-commuting operators, which is very important because most of the terms that we've learned so far, eigenfunctions, observables, operators, are interlinked. We need to know them to continue with our study of quantum mechanics. So we are going to make a quick revision on commuting and non-commuting operators. We made mention that if we have two operators A and B, A operated on B, AB minus BA gives us 0. If we have two operators A and B, and we are operating them on a function, does the order of operation affect the function? And we said, let's say if our function is f of x, and we have AB. This is to tell us that we are operating B on the function first before A on the result that we get. And the same thing if it's B operated on A, this is telling us that we are rather operating A on the function first and operating B on the result one, which means basically the operator that is next to the function will be operated on the function first. So we said if we operate B on the function, the function followed by A, and the other one we operate A on the function first followed by B. If we get results which are the same, let's say here we got X and here we got X, then the difference between AB and BA should give us 0. That is not to say it must give us 0. But if AB minus BA gives us 0, then these two operators, A and B, they are commuting operators. They do commute. And then if they do not give us 0, it means the two operators do not commute. And we said the reason why we are studying this is that in our study of classical or quantum mechanics, you might want to measure to predict the position and the momentum of a system at the same time. So if that is what you want to do, you have to look at the momentum operator and the position operator, operate them and see if they are commuting operators. If they are commuting operators, it means you can measure the position and the momentum of that system at the same time, simultaneously. If they do not commute, then it is impossible. Now, let's pause here. We will continue from here later. You can also feel free to check a video on this. This video is part of a playlist called Quantum Mechanics. Now, in classical physics, we deal with positions, linear momentum, and other observables regarding them as functions of time. The time evolution of a system is calculated by solving various equations and reporting the results as the functions. With respect to time. For instance, in classical mechanics, we measure momentum with respect to time. You see how momentum changes with time, right? That is what we do. And if we are talking about position to, let's say, xt, how it changes with time. This is what I meant by in classical physics we deal with position, linear momentum, and other observables regarding them as functions of time. For example, in classical physics or mechanics, a particle of mass m a particle of mass m undergoing a simple harmonic motion, the basic equation is the Newton's second law. Newton's second law, which is reported easily as m d squared over d t squared x equal f. Now, what we are doing now, you can try to memorize them or you can decide to leave them because we are starting from somewhere to go towards, another place. And this equation, we can name it as equation 1. And with the force proportional to the displacement, we also have the force to be equal to minus kx t. You don't have to bother as to driving these equations here. We just want to get somewhere. So as we know that this is a force and this is also force, which means we can equate this term right here to this term. So m d squared over dt squared x can be equated to minus kx t. So now in simple harmonic motion, solving this, the solution of this relation gives a linear momentum of the particle, say p, linear momentum p of the particle to be mx t, which can also be represented as minus m a omega sine omega t, where a is the amplitude of the wave and omega is the angular momentum. The same solution of this relation give x, the position changing with time to be equal to a cos omega t, where omega, the angular momentum, equal k over the mass square root of this. We can say p with t, position changing with time, momentum with time, position with time. So according to classical physics, if we multiply, let's say, xp, the result that we get, it will be the same as multiplying p by x. So if we transfer this idea of commuting and non-commuting operators, if assuming x is a position operator, p is a momentum operator, if we multiply x by p, the result that we get will be the same as p by x, which means that xp minus px is going to give us 0. And if you are to transfer this idea to our commuting and non-commuting operators, if xp minus px gives us 0, it means the two operators, which is momentum here and then position of the particle, do commute, which means we can measure them at the same time, simultaneously. Right. That's the main idea of commuting operators. If the two operators do commute, then they can be measured simultaneously. And classical physics gave us this relation to be true. Well, this p and x, if we multiply x by p right here, the relation we are going to get is minus m a squared omega cos omega t sine omega t. The same thing, if we multiply p by x, we are going to get the same thing, which means the difference between xp and px will give us 0, which means they do commute, so we can measure them simultaneously in classical physics. Then, what did Heisenberg or according to the Heisenberg constitutive principle. What does it mean? Heisenberg said that these two operators, like we cannot get zero in quantum mechanics. This is the idea that matter waves, assuming the particles in the subatomic level are in constant state of waving, knowing the position and the momentum at the same time, or predicting the position and the momentum at the same time, simultaneously, will be somehow strange. So it means if we have the idea that matter waves, this shouldn't be the true equation. So finding the true equation turns out to be the same as finding the Schrodinger equation, which is a fundamental postulate of quantum mechanics. Schrodinger said this quantity here shouldn't be equal to zero. It should be a non-zero quantity, either being small, it should be a non-zero quantity. But according to classical physics, these two operators do commute, so it is possible. Heisenberg said it shouldn't be possible this way. If we have the idea that matter waves. So what is the true equation? So now, this is what we are trying to say here. Let's say the true equation xp minus px, it should be equal to a non-zero quantity. This should be our true equation in quantum mechanics. And this is the fundamental postulate of quantum mechanics. And you can call this the commutation relation. The commutation relation. An immediate major implication of the commutation relation is that x and p, which is our position and momentum, cannot any longer be regarded as functions of time for now. If we are saying that, or if we assume that the position and momentum of a particle cannot be measured at the same time, then for now, p and x are no more functions of time, like functions of time, like pt, x with t. Because in quantum mechanics, we know that we don't deal straightforward with observables. We are rather dealing with a wave function that has the probability of telling us the value of our observable, which is the eigenvalue. So now we can rather say it is our wave function, let's say psi, that will be working with time and then x. But this is not to say it always. Just an assumption for now. In quantum mechanics now, we assume that if you are dealing with these as operators, it means that these two operators are time independent, but the wave function carries the time dependence. So instead of p with t, x of t, we will have our wave function to be xt, because our wave function is going to tell us what exactly or something is going to help us assume the behavior of the particle that we are talking about, or the system. So now, because quantum mechanics does not describe particles using ordinary numbers like in classical physics, we need to describe, but rather describe physical quantities as operators acting on a wave function. Then let's see how we can play around this commutation relation, which is xp minus px equal I h cross. So assuming we have a momentum operator to be p, or something that is related to momentum to be p, let's say for a particle in the x plane should be changing with respect to, let's say, x, but we should have a certain value that it will give us, let's say a, and the position of our particle to be x. So now what we want to do is that to find out, try working around this equation. So let's say we have, assuming we have two operators now, we want to find x multiplied by p minus p of x, multiplied by x. It should give us some quantity, which is I h cross. Heisenberg is saying this shouldn't give us zero. And we know that quantum mechanics describe physical quantities as operators acting on a wave function. So let's say these are operators, the first term of our operators and the second term of our operators. They should be acting on a wave function, which we know has some information. Right. So what we want to do now is to try fixing these values and see how our equation is going to look like. So we are going to have the first operator x multiplying px, which is a d dx. A, since we are dealing with, okay, d dx, including our wave function, and then px, which is a d dx. The minus signs should be here, a d dx, and then our x, which is just x, and the wave function should be there. Right, it should give us some term right here, and the wave function should be there. I recommend you watch our previous videos or try to get some understanding about eigenfunctions, operators, and observables, and a lot of stuff which might help you understand things here or somewhere easier. So now what do? We have two terms here. This term right here is in bracket, which means we are finding the derivative of x and the wave function. X multiplying by the wave function. Initially, let factor a out. So we are going to get x a d over dx, the wave function, minus a, we are factoring a out, into bracket, d dx, into bracket, x multiplying the wave function should give us I h cross the wave function. We are actually going to differentiate this using the product rule. If we have of two functions u and v, then the first one should be, let's say, u d over dx with v plus v d over dx u, right? That is exactly what we are going to do for this term right here. So in this case, differentiating this whole thing, first of all, with respect to x, we bring our wave function here, and differentiating x will give us 1, which means we are basically going to have only psi here, right? And differentiating with respect to psi is going to give us, we have the x here, multiplying d over the x psi, which we don't have any x term to differentiate. So it's just going to give us the same term as d dx psi, equated to I h cross or h bar, the wave function. Don't forget that we have a here minus, and we still have x a d over dx psi. Here, the differentiation sign is only affecting psi, not x and those, and a here. Right, we can put this here. So let's continue with our calculations. Okay, now let's continue. So x a d over dx psi minus, let's expand the bracket. So minus a by psi will give us a minus a psi, minus a by x dx psi is going to give us minus a x d over the x psi, equated to I h cross psi. So what do we see? Looking at this term here, we have xa, we also have xa here, d over the x, d over the xi, d over the xi here, which means we can cancel this term here right out. This is a negative sign, negative one, and this is a positive one. So we can just cancel this and that. Remaining are minus a psi equal I h cross psi. So from the formulation, we said this would be our momentum changing with respect to x. If we are talking about 3D with respect to x, 1D. If we are talking about 3D, our momentum might be changing with x, y, z to t if we are talking about 4D. So now, it means that if this will correspond to our momentum value, momentum term changing with any of the axes, then let's start comparing this side to this side. We are to compare both sides of the equation. So if A is the momentum, then it means that the value of A here, the term corresponding to A here is going to be, so minus A is going to be I h slash. We have psi, which is the wave function at both sides, so we don't have to care much about that one. So our A is basically going to be this. So this is for A, and so now we can see that our momentum operator now, Px, or let's say P, is corresponding to A, which is minus I h slash d dx. Right? And h cross is the reduced Planck constant. Reduced Planck constant, where I is equal to root of -1, square root of -1. So, and the relation, the reduced Planck constant, h cross equal to the Planck constant divided by 2 pi. So in this case, you might have different form of this same operator here. That is, the h cross can be replaced by h over 2 pi in some places. So j equal root of -1, and mathematically minus j, I minus I equal 1 over I. So if you are to replace the corresponding term for minus I here is going to be I over, so 1 over I H cross D over dx, which will give us our final momentum operator to be H cross over J D dx. So any of these, you can come across, any of these formulation for momentum operator. Either this or that, or the one in which the H cross will be replaced by the Planck constant itself. And this indicates that, it indicates that we have correctly defined our operators. And this is the derivation of momentum operator in quantum mechanics by using the fundamental commutation relation between position x and the moment. It is very advisable to know these operators. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye. Because as we move on, things tend to be somehow tougher if we don't know these things. The hygiene, value equations, observables and operators, and the other terms in quantum mechanics. That is it for this video. If you have anything to comment, the comment section is there for you. And feel free to support this channel by liking or at least sharing. See you in my next video.